Hi, welcome back. This is part B of homework number three. And the problem statement states via an energy balance, derive the relationship Bernoulli equation between inlet 1 and outlet 2, pressures P, heights Z, average velocities V, internal energy per mass U, flow a steady state flow system with heat and non flow work inputs per mass flowing through the system of Q over M and W and F over M respectively. Emphasize in particular the origin and role of injection work in your derivation slash explanation. So I'm going to draw a diagram to start this problem off of our system. So we're going to have a pipe, a circular pipe, and in this pipe we're going to have flow coming in and flow exiting. And we're going to call this our one, our inlet, and our outlet two. Um, and this will be our system, the flow inside. So we have our mass of the system multiplied by the internal energy per mass of the system, which is U, plus the potential energy per mass of the system, GZ, plus the kinetic energy of the system, which is V squared over 2. And we want the rate of change of this, so we're going to do d, put it over dt. And this will be equal to our inlet, so we have m1 dot of u plus gz plus v squared over 2. And remember, this is the internal energy, potential energy, and kinetic energy. Um, Minus m2 dot u plus gz plus v squared over 2. And then we can imagine there's heat being added here. So we also have a pump that is pushing the flow through, which is a non-flow work. So we can um, add non-flow work to our system plus heat flow, which we're going to call Q dot. Um, and then there's also injection work acting. And what injection work is we could think of it as adding a or the work it takes to add a certain volume of our fluid to our system or push into our system. So say we have our pipe here and we want to figure out how much work it'll take to add this volume of fluid. We have our area here and a pressure force, and we're going to call this X. So our injection work is going to look like P V, or sorry, P A X, and area times X here will go to a V, so or volume. So we have pressure times volume. However, we need this in a form of a mass. So we have pressure um, mass over density because volume is equal to mass over density. And this will be equal to our injection work of P over rho m dot. So we're going to have plus P1 rho m dot minus P2 rho m dot to account for the injection. It's now time to do the energy balance, and our system is in a steady state. So we have 0 is equal to m dot u plus gz plus v squared over 2 plus p1 over rho. And this is our inlet plus, or sorry, minus m dot plus gz plus v squared over 2 plus p2 over rho. And this is our outlet, plus our non-flow work, plus the heat transfer, or heat flow. And most of the time you won't see it written like this, so we're going to get P2 minus P1 over rho plus G times Z2 minus Z1 plus V2 minus V1 over 2 is U1 minus U2 plus WNF over M plus Q over M. So we have our pressures over our density being our injection work plus the potential energy per unit mass plus the kinetic energy plus the internal energy, or equal to the internal energy plus non-flow work over mass plus heat flow over mass. And when this side is equal to 0, this side remains the same. We call this scenario, or this equation, the Bernoulli equation.